Sorry, got it. I have to press. And yeah, so this is a joint work with Chris Culp, Mihir, Gandhi, and Yoshio. It's been a little bit stalled by COVID, but this is a good version. You know, it's been around for a little bit, but we reshaped it a bit. So let me tell you what we do in this paper. And essentially, we introduce two new quantities to characterize option prices. And then we use them for something. So the first one is what we call the option-implied spread. So this is a spread of options implied bonds. So I'm going to tell you in a second what the implied bonds are, but for every put option, you can get an implied bond. Actually, here is the little equation. And you know, this is just to tell you what we do. And so we study this guy here. This is not new. We already did that in a different paper for a completely different reason, to study credit markets and the relation with corporate bonds. But you know, in this paper, we are going to instead use the same measure for studying options. The second one is, you'll see why, is a normalized option implied spread. So essentially, we take the implied spread and we divide it by essentially the risk neutral default probability default, where default is the implied bond, is that guy who actually can default. And so you will see, you know, these two things actually have very nice properties and the dynamics and the cross-section, etc., and can be used to study a number of things. Again, in a previous paper, we studied credit markets. This one, we can study options. And so the idea of the paper is really to use the insights from corporate bonds that for which we know a lot. There's been a lot of research in the past to characterize the dynamics of option risk premia. And I will show you, you know, this is essentially an empirical paper. So, you know, there is at the end a model to rationalize our results. But the idea is that we will be able to use these insights essentially to give some explanation of what we see in the data. You know, the crucial facts written here. Essentially, what you will see is that implied bonds returns are strongly predictable, exactly like you have corporate bonds returns are predictable, from actually the work of Yoshio, one of my co-authors. Instead, it's very well known that put option returns are unpredictable. You don't know how to predict, you know, the future returns of put options. It's a very known result. It's been around since forever. However, you know, it turns out these two things are linked, and so we are going to use the notion of corporate bonds to try to understand why these 1 and 2 actually happen. What is it that is going on? It turns out that, you know, in our structural model, you know, time varying volatility, jump intensity actually turns out to rationalize both facts. But that's essentially in a nutshell what we do today. Okay, so that's the outline. So let me just jump into it. You all know, I would assume, that the famous 1974 paper from Merton, you know, corporate bond is equal to a risk-free bond minus put option. So whenever you think about a corporation, you think about the corporate bonds as at least theoretically one way to think about it, you know, risk-free bond minus put option. And then you use option pricing formula, Black-Scholes, you know, Heston's, whatever it is to compute these numbers, and then you get a corporate bond pricing. In our AR paper, in previous paper, essentially said, well, you know, we can actually do something else. We can look at the real traded option, so the one that for which we have prices. Risk-free bond is observable, so we get this notion of an implied bond, something that really doesn't exist, but is implied by put option. But then from this implied bond, we can study its properties and especially the credit spreads. The AR paper was all about credit spreads, and we show a bunch of stuff there. And, you know, in formulas, you can imagine, you know, the implied bond is equal to, you know, Z, you know, a little before notation. The risk-free bond is a zero coupon bond, so Z at time T with maturity capital T, minus a put option, you know, I'm going to denote it this way. K is the strike price, T is the maturity, and T is, of course, the time. You know, put in level of strike essentially is as if a bond has been issued. You know, a corporation issues some amount of zero coupon bond with face value K, and then the value of that bond would be equal B times K, but then, you know, we redivide to have it in percentages. From this, then everything, this is a bond. So you can compute the yield, continuously compounded like anything else, and the credit spread. Okay, the credit spread is the yield, the one that you compute from continuously compounded, minus the equivalent yield for a zero coupon bond. So it's RT capital T. And then if you substitute, this guy was over here, you plug it in there, you end up with this pretty simple formula for implied spread. That's the first thing that I would say, so in this measure we are going to propose, I show it in a picture in a second, it's 1 second to compute from put option. You don't have to have a Black-Scholes, search formula to find out the implied volatility, which sometimes if there's some violation or arbitrage, you can even get the number. This one is trivial. It's a put option divided strike price 1/z. You come up with the implied spread. Very, very easy to look at. You can do it with a calculator. So here's an example. October 6, 2017. Why the date? Because we were writing the paper at the date. Was actually absolutely no reason whatsoever. But just to give you an idea, take the date of the day of put prices, and from that you can compute the implied volatility, standard things you do from Black-Scholes formula. What we say is that rather than doing that, another thing you could do is to look at implied spread. So you end up with something that looks like this. Okay, so on the x-axis here, there is moneyness, so how much you are out of the money or in the money for put options, and the maturity on the other axis. You see that is a different translation. Here, the put prices, you can compute implied volatilities, which we all know are very familiar with, or implied spread. Implied spread is a different notion. The implied volatility is a notion of risk of the stock, even if there is all the complication and the difficulty of interpretation you may have. Implied spread is like a bond. Okay, so we know what bonds are, and so that's how it works. Now, if you look at this, though, there is this problem that for very short-term options, the implied bond is essentially certain to default, meaning that you end up in the money. And therefore, the implied spread is going to diverge to infinity because, it's the risk goes to infinity, essentially. And so that's no good. We want to renormalize the implied spread by the probability of default. Okay. And you remember that from put prices, you can compute the probability to be in the money. It's actually something that has been known since forever. And so that's what we're going to do. We are going to simply compute the probability that the stock, these are put options, so it's in the money. As you know, you can just take the first derivative with respect to strike prices, discounted to today. Is a standard formula that doesn't require any model. It's just no arbitrage. And then this is a number. We want to convert that in an average over time. A yield, even if the payment is a maturity, it could be 10 years to maturity, zero coupon, means you don't get anything for 10 years, but yet you can still compute an annualized return. Well, we can do exactly the same for a probability. Default is going to be only a maturity, but we can compute an average default frequency by just using the standard methodology. So we compute the annualized implied default frequency, which is essentially translating this number here, the probability to be in the money, which incorporate bonds means to default, into an annualized number, which turns out to be this formula here. Very straightforward. You may notice the nice symmetry between this formula and the one for the credit spread, because the credit spread, instead of having dp over decay, is going to be only p over k. So this is the first difference instead of just the levels. But otherwise, the two formulas are identical, which is a nice symmetry. And so the normalizing implied spread is the ratio of the two. Okay, and that's what we define it in normalization. Essentially, the implied spread in units of default probability. This is neutral, of course. Okay, so it's a different type of unit. And I'm going to give you an interpretation of this. However, if you plot it, you end up with something like that, which is much similar, well, at least in terms of how it looks, to the implied volatility. Is between 0 and 14%. Again, these are in units of default probability, and has a little funny shapes here and there due to the data, and it's another measure. Very, very easy to compute. The only difference compared to implied volatility is that any number here depends on the value there of the put price and the two around it, because you have to take the first derivative. That's it. Okay. What we're going to do is to study these two things. Okay, I'm going to show you a bunch of plots, a bunch of regressions showing what these two measures do, and we'll compare them, of course, with implied volatility. Okay, so that's the plan. Okay. I have another formulation for NIS, well, for this normalized implied implied spread, sorry, which is, it turns out if you substitute, you end up with this formula over here, where X is the, you can call it leverage if you are thinking about this as a bond. And so LGD stands for loss given default, literally. And then the second term is expected default probability. All is neutral. Actually, in this case, under the forward is neutral probability. And let's say risk adjusted. Let's see it there. So if you look at this formula, this is exactly equivalent to the previous one. It's not a model here. It's just retranslating. Then actually you have this implication that this NIS, this normalized implied spread, increases with the loss given default. Okay, in fact, it's 0 if LGD is 0, and it's 1 if LGD is 1. Okay, you can see from this simple formula. So first of all, you see that it's increasing, and in these two quantities. In addition, for given LGD is decreasing in the expected probability of default. Okay, then of course LGD and E are not independent, so you can't really do this thought experiment to change all the distributions. But if you see what I'm writing here, NIS is nothing more than a measure of tail risk. Okay, for given probability of default, which is the second term here with the star, the bigger the tail, the bigger is the LGD in expectation, or under risk-adjusted probabilities, the bigger is NIS. Okay, so one way to interpret it very nicely is as a measure of tail risk. In this paper, we don't do very much with it. We just use it as a right-hand side variable and run a regression. But I can imagine other papers being written about this tail risk distribution. So we use it for something else. Having said that, let me show you some data here. This is just an example instead about what happens to all these quantities during good and bad times. And so, in our sample, we have two big crises. One is the financial crisis on the left axis. The other one is the COVID crash on the right-hand side. And you see that everything moves exactly as you expect implied volatility does. So the top is implied volatility, and we know that implied volatility went up in both cases. Well, implied spread do the same. Okay, they just went up with the crisis, and the same the normalized implied spread. Okay, so they behave qualitatively like the implied volatility. In bad times things get worse, and so they get bigger in a sense. Everything gets higher. Notice that implied spread will always have this shape. If they go up with moneyness, it has to happen. This has nothing to do with the smirk or anything like that. It has simply to do with the fact that when you are on the right-hand side, the probability of default is higher, so credit spreads go up higher. And so that's all it is. So the spreads gets bigger at higher, the more you are in the money. And one question that is important in order to understand these measures is really, well, what do they look like in standard models? So here's a couple of plots. You have the Black-Scholes-Merton model, the standard one that we all teach to undergraduates and MBA students. And you see that, there's nothing really to see. The higher volatility and the higher is going to be the implied spread. Nothing really surprising there. And as I said, everything is going to go up because, again, higher probability of default on the right-hand side. Normalized implied spread is kind of interesting. Normal distribution implied not really a straight line, implies a little bit of concavity. This means that if you don't have much tails, actually this measure, it tends to be a little concave. So we're going to compare that to the data later. Another standard model could be this one, the standard Merton jump diffusion model, the standard one with constant probability of jump. Again, nothing really happens on the implied spread except that a higher risk, a higher spread, exactly what you expect for corporate bonds. Here is interesting, the normalized implied spread. So remember, the normalized is the implied spread divided by probability of being in the money of the default. Actually start looking weird. Okay, so you see that the probability of a jump, in fact, increases the normalization. Essentially, this model would imply that the implied spread per probability of being in the money increases the more you are out of the money. So it's a convexity due to jump risk. So later we're going to see the data. We see that there is this convexity in there. Okay. Again, this is kind of benchmark for you to see what this doing standard model. Let's look at the data. Okay, so the data is the standard one on S&P 500. I should have written it here, sorry. The S&P 500 options data from 1990 to 2020, in last year. So it's a very long 30 years data set. And these are just averages so that you see what it looks like. So the implied volatility, we all know how it looks like. There is the smirk here in moneyness, and then the time to maturity on the other axis. The implied spread are on the B panel here, you know, exactly what I said before. They go up in for shorter maturity become very large, and then, you know, they go down as the maturity increases. Standard, very similar corporate bonds, and nothing really surprising there. The implied default intensity looks like this. Notice it looks almost the same. Okay, so of course, the more you're in the money, the more likely you're going to default. You know, so you know the two things go together. So when you divide them, you know, the average ends up being something like this. So this area here is the ratio of these two, and you see the little convexity I was mentioning before. Okay, so it looks like it's not normal. There is convexity. This normalized implied spread, you know, as you go to the left, you know, it looks a little bit concave. That indicates, on average, some jump risk according to the previous model. And later we're going to estimate a proper model, but just intuitively, it looks like it's coming from there. Okay. These are averages. We can look at booms and recessions. I already showed you a kind of a plot with the two big booms and recessions, so this is not surprising. Let me move on. And this is a time series. Okay, the time series across the top two panels implied volatilities, either with constant maturity and different strike prices, or different same strike price, different maturity. You know, they go up and down. We know what happened in 2008, the big spike during the COVID crisis, etc., etc. Implied spread, you know, they look different simply because if you think about implied spread, if you have different strike prices, is as if you have different leverages and therefore different level of spread. So the yellow one are the junk bond, and the red ones are the AAA bonds. If you want to think about corporate bonds, of course, it's a term structure of corporate spread or implied spread, which will depend on leverage. Okay, that's just the difference between one and the other is leverage. They go up and down. If you say keep leverage the same and only maturity, you know, you see a little more the shape going up and down. Similarly, normalized implied spread, now they start really looking like implied volatility. They all cluster together. Okay. So how are these three series correlated with each other? We can do a principal component analysis to look at the PCA of implied volatility across all series, the PCA of implied spread, and the PCA of normalized implied spread, just to see also the shocks, whether they're the same shocks, they're different shocks, they're highly correlated. You can tell they are highly correlated by just looking at this. But again, you know, we do it just in case. So these are the principal components of implied volatility is the blue. The red is implied spread, and the one at the bottom is the normalized implied spread. And they move up and down. They're highly correlated, especially the one implied volatility implied spread. They essentially contain the same information. You know, there's a little bit more juggle here, but they are very similar. You will see also in the regression later. In fact, the correlation between implied volatility and implied spreads is 90%, whereas in first difference, 80% is still pretty high. Now, you see that in first difference, instead of normalized implied spread, the implied spread are actually not that correlated, which indicates that the type of information is different. The shocks may be different. Okay, and so, you know, it's again risk to rewards, and this is about risk to rewards. Okay, rewards to risk is amount of yield compared to the default probability. Should I answer the question, Jan? Forgot whether what we said. You gave the rules before.
Yeah, Jan, go ahead.
Yeah, so this was just a clarifying question. Are these are calculated for S&P 500 options?
Yes, sorry, these are all S&P 500 options. In our JP, in our AR paper, we use all the options, also individuals. This is just those ones.
Okay,
Yeah, I should have
perfect.
mentioned
Thanks.
that, sorry. Anyway, so these look, if you remember how easy it is to compute implied spread compared to implied volatility, and the fact that they are 92% correlated, gives also an indication that if you need to compute it quickly, you don't need a computer, you need just a calculator, given the high correlation. This paper is about predicting returns, and that's where we are really departing from our previous work. We didn't look at returns at all before. So we are going to have 3 types of return, but really only 2. I'm not going to really talk about this one. The put option excess returns, so it's return on options minus the risk-free rate, the monthly frequency, and then the implied bond excess return, which again, for every bond, every put option, we can compute the bond, and then we can compute the bond tomorrow minus the bond today divided by the bond today. And we can compute the return, the excess return on that bond. By the way, there are traded securities, even if we do use, quoted prices, okay, in honesty. So these are all about quoted prices, but there's the same on the top and the bottom. So it's the same type of mid prices. And then we do what we normally do. When you have returns, you try to predict them somehow. Okay, so, here are some summary statistics. We all know the summary statistics for put returns. Of course, the expected return, the average return are negative. These are moving opposite to the S&P 500, and pretty high Sharpe ratios. The implied bonds on the right-hand side here, you see Sharpe ratio are not huge. Okay, there isn't an arbitrage violation, etc. They are 0.3. They are kind of comparable to corporate bonds. 0.3, 0.2. Depending on the moneyness. Here are different moneyness. And here are different maturities. That's how they look. Okay, so some summary statistics. Notice that don't have much volatility. If you have a volatility of put options, talking about 76% as an example at the money, is 2%. Okay, so they are not volatile. Most of it is actually the zero coupon bond, the treasury, but still they're volatile. They are not safe. So what we do, we run this regression, okay, excess return over implied quantity to get it started. And here, honestly, we took off from a paper by Brian Kelly in Israel, I think, or somebody, and about predicting the excess return on put options. We just do a gigantic pool regression just to see how B looks like. Okay, so we put all the data on the left, all the data on the right. And the first one, even without control, we get something like this. Okay, so there are a lot of numbers here. So let me just walk you through the various columns. The top is the implied quantity. So it could be implied volatility, implied spread, or normalized implied spread. So the right-hand side are written over here. And then the left-hand side is each column. So we are regressing put returns on implied volatility will be this first column, or implied bonds on implied volatility will be the third column. And we do it across all combinations, just to see it. I'm going just to give you a sense here by just highlighting some things. There are some things that are significant. Okay, so you see that there is some predictability of puts, some predictability of implied bonds. Although if you look carefully, R square, this is a pool regression. Remember, there is a bunch of stuff here, cross-sectional, time series, everything is in here. 0 for put options, 1% for implied bonds, not much there. Normalized implied spread, moreover, are noisier, so nothing in there too much. Put control, things get better. Controls are like moneyness, time to maturity, gamma, vega, etc. I'm highlighting things that are significant for you just to see. One thing that is the takeaway is that the things on implied bonds are better to predict than anything else. Okay. You see that the R square increases much less for implied bonds than for put options, meaning that all the cross-sectional information is more important for put option than for implied bonds. Again, it's not too surprising. In fact, if we look at different buckets, you can do just out of the money, at the money, in the money, and for the 6 maturities, you see that only implied bonds are remaining actually significant. Everything else drop out pretty much. Maybe a little bit here, but there's nothing left. So implied bonds are pretty strong. So the bottom line here is that it looks like there is some predictability for implied bonds, which would be consistent with corporate bonds. In fact, we can do a little more. Is this predictability economically significant? And compare that with put options. Okay. So how do we compute that? We stole this idea from John Cochrane. And so you compute the volatility of the expected return from the regression. And then you take the ratio of that with the average return you want to predict in the data. And you see that this number here is tiny for put options. It's like 0.09. But for implied bonds, it's 0.7, which is completely comparable to the number. This is a number that is coming from John Cochrane. I should have put the number here. This is from a JF paper on John Cochrane. You see 0.7, is the predictability of stock returns at the annual level using the dividend price ratio. It's about the same. Okay, it's the same level. If you look at corporate bonds, actually it turns out it's even higher than that. So, but it's still there is significant predictability. For puts, not much. Okay, again, it's a non-result, but we are corroborating. Okay, one thing that you may notice from this table, just going back 1 second, is this coefficient. It's positive here, and it's positive there. Okay, in other words, if you interpret this coefficient, they are positive in both cases. It's kind of weird because it implies that higher implied spread implies higher implied bond returns. That's intuitive. That's what happens in corporate bonds. However, it also implies higher put option returns. It's weaker, but it goes in the same direction. But it's weird because remember, one is short the other. They don't go in the same direction. So if you remember, if you take the put option, you can rewrite it as minus the implied bond plus z. So one is long, that is short. They have different signs. It's weird that if you run the regression, both of them get a positive sign. Okay, so we were puzzled by that. It's going to come important later. And so it turns out that after you think about it, it's not that puzzling. But if you think about the expected return on implied bonds is intuitive, the fact that a higher implied spread implies higher expected returns, then what's going on with put options? Well, put option is a portfolio of zeros and implied bonds, where this is negative, this is positive. However, the weights are not constant. And that's what happens. Essentially, what happens is that there is an ambiguous relation between implied spread or implied volatility and the put excess returns. If you think about higher implied spread may increase higher bond returns, as happened in corporate bonds. On the other hand, this would imply a lower put return because it's a negative sign. So everything else equal, that would push it down because this is negative. Sorry, this is positive overall. On the other hand, A changes. The way that you give it to the two components changes too. In fact, if implied spread increases, the weight on A goes closer to 0. So this term disappears if you want, and so you give more weight just to Z. Okay. And so, in fact, we can use that insight to have a joint, to show that actually there is time varying risk premium. We use a test of joint predictability. Essentially, we test these two hypotheses. So this is the usual idea, when you look at precedent ratio and you're doing stocks, you see a precedent ratio move up and down. Something got to be predictable because otherwise it wouldn't move. The same thing here, the return on implied bonds is the weighted average return on zeros and return on puts, but the weight is time varying, okay? And we see in the data I showed you before, the implied spread, if you look at the weight, it can be written as implied spread times something. The implied spread is moving up and down, so it's impossible that these three things are independent of the implied spread. One of them has to depend on it. Maybe some cut edge situation, one cancels the other, but it's very unlikely. So the point is, suppose that the return on zeros is independent of implied spread, which would be intuitive. Then if the return on put is not predictable, it means that the one on implied bond has to be predictable. Vice versa, if implied bonds are not predictable, it means that the one on put option has to be predictable, because otherwise it's a violation of an identity, which it can't happen. Okay. And we test that, and indeed we find, just to make the story short, that we strongly reject no predictability by imposing this joint null hypothesis. Okay, this joint null hypothesis allow us to really document that there is predictability in options data. Okay, is just coming from here, again, using only short-term data. The way we do it is to use Monte Carlo simulations, just to one word, and simulate a bunch of numbers by running the regression under the null hypothesis. And then these are the p-values that would come out from that exercise. These are all zeros, which means essentially you reject. Instead, for the other hypothesis in which there is no predictability of put, but predictability of implied bonds, we can't reject. You see that these numbers are pretty large. Maybe this one, this on the slope. We do the test of Boston slope on theta statistics. Anyway, so again, what is it we are doing? We are using option prices, these implied bonds, to try to detect some predictability and to try to understand what's going on with put option, why they are not predictable. Well, because implied bonds are predictable, like you have in corporate bonds. And therefore, it could be, well, that RP are not predictable. Again, I'm going to tell you more in a second about this. Then we do long horizon return predictability. Okay, so suppose you buy an out of the money option, and then the next month you sell it, you buy another out of the money option. So you keep rebalancing, keeping constant the moneyness. That's important. So if you have good stocks returns and you buy an out of the money option and then become in the money, it's not going to be the same contract. We literally keep rebalancing every month. You sell the one that you have and you buy the same out of the money option. And you keep doing that, and then you predict it using something on the right-hand side. Again, could be implied volatility, implied spread, or whatever it is. And you do it for different horizons. What we got was stunning. Okay, so these are a lot of data, a lot of numbers, but I just draw your attention to the t-statistics. Okay, across the board, again, we are computing implied return predictability only for implied bonds, long-term up to 1 year. So it's not 20 years like stock prices. They're all strongly significant with a very strong R-square. 15% for 1 year is actually pretty good. In fact, if you use implied spread for implied bonds, which is the natural thing you would do for corporate bonds, you get all the way to 20% predictability R-square for strongly out of the money options. But even if you are only 5% out of the money, it's still 10%, which is very sizable for 1 year predictability results. So there is a strong predictability of implied bonds, as is actually pretty clear. Wherever you see, it's the same. What is stunning? Then you can do the same for put options themselves. Okay, let's do it. And there is nothing, literally nothing. It's the same regression. We just changed the return. We put instead of implied bonds, all zeros. There is nothing significant, not even one by coincidence. And it's amazing in the sense that we do this because of this portfolio. Then you had all that return predictability. You do for puts, there is nothing there. Okay. And then we were kind of stunned. This is known actually. We already knew it, but we really document this difference between implied bonds and put options. Okay. So, this really shows a puzzle here. Again, the puzzle is not so much the put options are non-predictable, the fact that we already knew it from the literature, is why implied bonds are so strongly predictable when the put options are not. Given that there is a tight relation between the two, the implied bond is 0 minus put option. Is a stronger relation as it can be. There is an identity here. And yet, using the same data, one is predictable, the other isn't. It's very weird. So at this point, we decided, well, let's go and look at standard models and see what happens. Okay. So, take a stochastic volatility model. Standard Heston and nothing with no frills, very, very standard one. These are under the risk natural, the physical probability. There is mu here. It is important. It's an expected return of stocks plus a bunch of stuff. Then you have, oops, sorry, went the wrong way. How do you go this way? Sorry. Then you give a state price density, standard one, again, very generic and nothing particular. This is a market price of risk of Heston, so that you multiply, square root on the volatility risk, and you end up with a really standard expected return risk premium. Okay, nothing new here. We wanted just to see what happens to risk premium. Okay, that's the risk premium, expected return minus risk-free rate. It's not just the drift, it's minus risk-free rate. And there is a beta versus expected return on the stocks. Then the risk premium for volatility, and then a jump risk premium. We didn't want to estimate all these, these investigative. So we take standard data from the literature, Brody, Chernoff, and Johannes, Chamberlain, Foy, and Liebner. Turns out that they do the same estimation with some little differences. We just use their parameters. Very standard. They did a bunch of, this paper by Brody, Chernoff, and Johannes has like 1 million sites. So we went with the standard things most recent. And this is what happens. And there is a formula for it. These are not simulated. There is a formula. The one that before is a formula. There is beta, mu, etc. There is no simulation here. But if you plot them, this is what happens. Look at the top, for instance. Well, actually, the middle. Let's look at the middle. You have implied spread on the x-axis. And so you see that this line is the expected return. Okay, yes, so implied spread go up, expected return on bonds go up. Okay, from using the standard estimate from the papers, we get exactly what we find in the data. There is a nice slope, higher spread, higher future expected returns. All good. And moreover, the more you go in the money, the flatter it becomes, meaning that if you are really in the money, then there shouldn't be any predictability. If you go back to the data, actually, you see that. The more you go to the money, the less predictability there is. Okay, so it's all good. It fits the data well. Okay, standard estimate. The downside is that those estimates has this other implication on the left-hand side, which has a higher implied spread should also imply higher excess return on put options. Remember that the returns are negative. Higher means, less negative. And that's using their estimates. It's not our estimates, it's their parameters, and you find this. And the same for implied volatility, you find it here, or a normalized implied spread. In other words, the Heston's model is completely counterfactual with these parameters to the fact that there is no predictability in excess returns of put options. You should detect it by running a regression, but you don't. It's not in the data. And so there is something that is not fitting here. We all know the Heston's model has a million problems, but there's one more nail in the coffin for that model. Nothing wrong against the Heston's model per se. It's just fact that there is one more issue in the physical measure. Okay, but this essentially calls that for the fact that the one factor model is a problem. Okay, this is essentially the same thing I said before. With only one factor, expected return on implied bond is tightly linked to expected return on the put option, and you don't have much wiggle room. So either they go up together or the one go up and down, but it's a one factor model. They should move together except for knife edge cases. Okay, so we tried other parameters. In fact, we did a gigantic extensive check. Again, it's not simulation. You can just put in the formula, and it works there. So the answer got to be a two-factor model. So but not all of them. We tried a few, and some don't have the right implication. This one does, and it's intuitive. So it's the one with stochastic jump intensity. So it's the same model, of course, but now lambda is a stochastic intensity, goes up and down, and state price density there. Let's skip that. And expected return now, this risk premium is the usual beta times expected return on the stock market, plus the volatility risk premium, the intensity risk premium, and the jump risk premium. They have a lot of them. Okay. But now you notice that there is a two-state variable, V and lambda, and so the plots are going to be two-dimensionals, and that resolves the issue. So we estimate, this time we estimate the model ourselves. Moreover, though, we estimate it, here are the parameters, using a little bit new methodology. It's maximum likelihood, pretty standard there, even if we have to use a little new model. Why? Because we want to incorporate in the estimation some moment conditions. Which moment condition? The fact that there is return predictability in puts, and there isn't there is predictability in implied bonds, and there isn't in put options. So we explicitly put some condition on that front in the estimation. Why is that interesting? Because it's gonna, the parameters are going to reflect also those conditions. I'm gonna go back to that in a second. Okay, what do we learn? We learn how those parameters, this condition affects the parameters. But before I do that, notice what happens. Okay, so that's almost the end of the talk. So there is an implied spread again, and there is now intensity on the one axis and volatility on the other. So V and lambda, but you see that higher volatility, of course, higher implied spread. We knew that, and higher intensity, higher implied spread. Think about corporate bonds. It's obvious. Higher intensity means higher probability of a jump of default, and therefore spread go up. We know it for corporate bonds. Higher volatility, more risk, more probability of default, implied spread go up. So nothing new in there. But now, if you look at the implied bond risk premium, indeed, they go up on both directions. So higher implied volatility or higher volatility or higher intensity, in both cases, there is an increased expected return on bonds. This is what we expect from corporate bonds. It's the same intuition. There's higher risk, higher jump risk. You lose money, tail risk. One of the contributions of our AR paper is actually to document how important is tail risk in the premium for corporate bonds, well, implied bonds. And this is just showing the same now in a model. Okay, so higher intensity, higher expected return. But now look at the put risk premium. Again, this is the model, and you see that, yes, higher volatility, higher put risk premium, what we know from Heston. But for intensity, that doesn't happen. In fact, if anything, either it's flat for high volatility, but if volatility is low, it's actually declining. So higher intensity, lower expected return on put premium. And then it flattens out. This flattens. So it's if you look, now it's in 3 dimensions, but if you look only from this direction, you see physical flat line or going up rather than going down. So it's really opposite to what you see for implied bond risk premium. Okay. So what is the intuition of that? Oh, by the way, so there's a plot. So what we did is run a million simulation and run the predictive regressions in simulated samples. And indeed find that with our estimated model, we find that implied spread predict implied bond returns, with similar coefficients as in the data, whereas put are not significant, as 0. The R square is 0, exactly as you saw in the data at the beginning. And these are the, sample by sample, essentially the confidence interval. So you see 0.0, this is 0. Instead, is strongly positive for implied bonds. So, our estimate, when you simulate the model, indeed generate that facts in the data. So we found a model that is consistent with this puzzling effect in the data. And again, what is the intuition? Intuitively, again, a higher volatility, you have a higher expected return on put options, less negative. That's standard in Heston's, was there too before, and a higher expected return in bonds. Very intuitive. But now think about higher jump intensity. Higher jump intensity increases the expected return on bonds, like you expect, is riskier. However, there is a hedge component for put options. Higher intensity, the put option become good hedges, which means the risk premium actually gets even more negative. Okay, and mechanically you would see it from this term here. Lambda is of course positive. This is a negative. The expected jump component here. This is a state price density. This is the jump is the put price. This number is positive. So higher lambda simply lower the risk premium mechanically. Is essentially an effect of insurance. Whereas for bonds is tail risk. So the two things are perfectly consistent with each other. And yeah, that's it. That's the contribution of the paper essentially is to look at options from the eyes from corporate bonds in order to learn something about options. Instead, again, in our earlier work, we look at the options to learn about corporate bonds. Here we go the other way. We want to use the logic of corporate bonds to learn about options. So I think that there is something that is new here, or at least that I personally didn't know. But after writing the paper, I got some better idea of what is going on. And I stop there, to answer a question. I think that we are more or less on time. Maybe not. Sorry if I went over.
No. I think you're like spot on time, even like a little bit early.
Good.
I do have some questions, but I feel like I want to just first see if there are any questions from the audience. So feel free to unmute yourself if you have a question and just ask it.
Can I ask you a quick question?
Go ahead.
This is Sang, by the way. So is it possible that the predictability does not show up from put option returns due to purely statistical reasons? Like, for example, option returns are extremely skewed. Probably there will be many negative 100% observations. So probably it is very difficult to predict future returns using a linear model, for example. So maybe this is not because of two-factor structures, or we need a different model. Maybe it is possible that you are actually converting these returns into the bond dimension, and everything suddenly started behaving very well in your predictability regressions.
Definitely, it is possible. Again, I wanted to have a structural model to rationalize this. I would say, though, that let me just go to the short term. It's good to have everything here so we can go back. When we did a pool regression, essentially you're throwing in a lot of nonlinearities. You know, it is, you know, very short term is in there, but it was there also when even with the one step, this number is 0. Maybe again, as you say, it's non-linear, and therefore it's 0. And once you throw in the nonlinearities, there is something in there, which is definitely consistent with what you just said. Okay, so it is possible. It's just nonlinearities. I do believe that you know, once you do these type of things that you put in bins and you have short-term maturity, there is not much. You know, there is no linearity, but it may play less overall. Maybe not. But you know, this is remarkable, though. It stays there independently of what actually you look at. And again, you know, the fact that these results are very similar to corporate bonds, and the fact that there is a risk premium just for tail risk, is kind of reassuring, right? You have two different markets with the same type of characteristic for expected returns. So I would be willing to say, well, okay, this is the true result. Now, how do we, now suppose that we have implied bonds and we compute put options out of the implied bonds, how do I supposed to behave, right? So because that's the question. But yeah, you know, that's a possibility, absolutely. By the way, I think one of my co-authors, both of them are online. If they want to answer the questions, you know, they're welcome to.
Hi, Pietro, Mike Chernov. I just wanted to add to this, right? So your picture when you were showing theoretical implications for a SVJ model, right? You had these plots. They kind of, yeah, that one, right? They already show that there is this nonlinearity, right? So, so that seems like could be a plausible explanation. So, but another point, a kind of suggestion, right? That given, so it seems to me like a sort of mechanically, right? You kind of found this magic transformation that makes this relationship linear, right? And that helps obviously. So when you're running OLS, it helps with predictability. But then the question is, now that you know that and you can predict this implied bond excess returns really well, can you take that prediction that you know kind of works and map it back into predicted returns for puts instead of running a regression for puts? Because right, you have this tight relationship between the two, right? So if you're saying, oh, I can predict one of them really well, okay, just take that prediction and map it back.
Yeah. That's a good suggestion.
How would that work?
I don't know the answer. You're right. So when we did the data part, we literally ran a regression. What you're saying is that now I have this coefficient and I have the implied spread. I have a formula. We should be able to tell you what the return tomorrow is. I know we have done something now. There was only simulation, I believe, when we did the joint test. That's pretty much what we did, but there was only simulation. I don't know if
it would be cool to see in the data, right? How well it does in the data, right? Yeah. And maybe that's a way to kind of get around this nonlinearity that potentially complicates things.
I remember also linearity came to our mind. I think we threw a bunch of stuff on the right-hand side at some point, like squared, etc. And nothing was really showing up as important. Again, Yoshio and Mihir is not here, unfortunately. So Yoshio is actually listening. I want to add on the empirical. We are all happy to hear your voice too.
No, so I just agree with what Professor Veronesi said. So basically what we did was to bunch this regression into smaller pieces to make sure that if there's any nonlinearity, we should be able to detect the change in slope because we are looking at the different segments of options. But that's all we did so far.
The suggestion, Michael, is actually very nice. We will see what that does.
Can I jump in too? So to me, this seems like a clever way to an alternative measure to volatility, implied volatility, and there is a big literature which tries to see whether volatility predicts future stock market return. So have you tried to see whether your measure predicts stock return? Maybe there is a chance because the regular volatility is just too noisy and your measure is just kind of in the beta units.
We did something for the AR paper, or at least when we were writing it, but then we moved that to only discuss GDP growth, etc., because it was related to another paper out there on corporate yields. Can't remember with Ryan. I don't think there is much in there, if I remember correctly. But I always thought that implied volatility doesn't predict any stock returns, right? I always thought that there was a puzzle that, and I also think that spreads for corporate spreads don't predict stock returns. It's one of those two puzzles. The reason why I know is I have this first class in my PhD class in which I actually do run all those regressions. I remember showing them regression returns or volatility or corporate bond spreads. There's nothing. And instead, if you put anything that has dividend divided by prices, earn divided by something that is divided by prices, it shows up with all the discussion of predictability. I don't think actually, maybe what you have in mind actually is something about the variance premium. Yeah, that one, where you expect returns on the Q minus P, but that's possible. But sorry, volatility and expected volatility Q minus P, and that we don't have a counterpart for this. But yeah, we haven't tried any of that. But I don't think. But I was not surprised not to see anything because I already knew that even corporate bonds don't predict expected returns, stock returns, at least not that I know.
Any other questions?